Hello children, I am Mrs. Apurva Kulkarni from Deccan Education Society's D.E.S.Secondary School, Tilak Road, Pune. And today I am going to take Science Part 1. In our previous session, we have learnt electric power, Joule's law of heating effect of electric current, magnetic effect of electric current, and right hand thumb rule. So today in this session, we are going to learn about magnetic effect of electric current, electromagnetic induction in detail. So let us move to our PPT. Now let us discuss this experiment. This experiment is set up is as shown in figure. This flexible copper wire stand, this is copper wire, okay? This is stand, electric cell, a horseshoe magnet with a strong magnetic field. All are arranged in this way. Now, whenever a current is not flowing, it remains straight as shown in figure. That is at position A. When the current flows from top to bottom here, the wire bends and goes to position C. So, wire will go to this position. Here you can observe the wire will bend like this. And if we reverse the battery, the direction of current will also reverse. The current will start flowing from bottom to top. As you can see here, the wire will come to position B here. So wire will move in this direction, that is at B position. It means the direction of force is perpendicular. Wire is moving, means force is acting on it. And direction of force is perpendicular to both magnetic field and direction of current. So we can observe this by reversing north pole and south pole of magnet too. This direction of magnetic field, current and force is given by Fleming's left hand rule. So what is Fleming's left hand rule? According to this rule, the left hand, thumb, index finger and the middle finger are stretched so as to be perpendicular to each other, as you can see in this figure. If the index finger is in the direction of magnetic field, the middle finger points in the direction of current, and then the direction of the thumb is the direction of force on the conductor. Now this picture is very familiar to you. Yes, it's electric motor. We know energy can change its form. We have learnt in previous standard. In electric motor, electrical energy is converted into mechanical energy. In our day-to-day life, so many uses of electric motors are there. It is used in fans, refrigerators, mixer, washing machine, computers, pumps, etc. But remember this basic thing, that this device changing electrical energy into mechanical energy. To understand the actual working of motor, this small activity can be done at home too. So children, you will enjoy doing this activity with the help of battery, magnet, copper coil, rubber tube, safety pins, as you can see here. The arrangement is done as shown in figure. When we give slight push to the coil, it starts spinning. The spinning direction of coil is given by Fleming's left hand rule, as shown in this figure. Now let us learn the construction of motor. This motor consists of rectangular loop of copper wire having resistive coating. This armature is placed in between north and south pole of magnet. AB and CD perpendicular to the direction of magnetic field. So direction of magnetic field is towards north to south. The two ends of this loop are connected to two halves, X and Y, of the split ring and tightly fitted on the axle. E and F, so those are carbon brushes which are in contact with X and Y. Battery is connected so as to give power supply. So this is the construction of motor. How does this motor work? Now, in the construction part, we have discussed. When the key is closed, here, the current will start flowing through E brush. A, B, C, D, like this, current will start moving. The direction of magnetic field from north to south. If we use Fleming's left hand rule here, middle finger is adjusted to the direction of current, index finger to the direction of magnetic field, then thumb will show downward direction, means AB branch will move downward and branch CD will move in upward direction, opposite to AB, because the direction of current in CD, here in AB it goes like this, and in CD direction of current will be like this. You can see here the direction of current is opposite. So AB will move downward and CD will go in upward direction. And axle starts rotating in anti-clockwise direction, as you can see here. Now after half rotation, the two halves X and Y of split ring come in contact with carbon brush F and E respectively. The direction, the path of current now will be F, D, C, B, A. So DC will be on AB's place and BA will be on CD's place. I'm talking after half rotation. So the force is exerted on DC in downward direction and loop continues to rotate in anti-clockwise direction. Thus, the current in the loop is reversed after each half rotation and the loop and axle continue to rotate in anti-clockwise direction. This is basic principle behind the motor. In commercial motor, some practical changes are made. So watch this video.
Working principle of DC motor is very simple. We can see that when the current conductor is placed in magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current-carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet, in elementary model. One single turn of conductor is placed between two opposite poles. If we start to supply DC via commutator system, current will start to flow. As we see, positive terminal of a battery is connected to left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left-hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is a line along direction of the current in right side conductor. Then thumb indicates direction of mechanical force. Due to this upward and downward forces on the turn, one torque is produced when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position there is no current in conductor because turn, conductor and brushes rest between two commutators. Hence, there is no force acting on conductor, by due to moment of inertia, turn continue to rotate and comes horizontal again. Position of conductor has been changed here. That means conductor which was previously in left position comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger, so they are all at 90 degrees to one to another. So if forefinger is a line in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is a line in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces, turn, tends to rotate in clockwise direction. From that explanation we can come to conclusion that, here in this model we can see that, whichever conductor comes near South Pole, experience upward mechanical force, and near North Pole, downward mechanical force. And do this continuously forces, mechanical turn rotate, even if battery is not connected. Particularly DC motor, rotates, at the same principle like this elementary model. Instead of single turn in DC motor we have mountain turns on major coil. And instead of 2 poles there is number of poles installed.
So now I hope you understood the principle and working of electric motor. Now let us learn about galvanometer. So galvanometer is a sensitive device which works on same principle as that of an electric motor that we have studied. We can make some electrical measurements with it. Here you can see galvanometer, voltmeter and ammeter. Voltmeter is used to measure potential difference and milliammeter is used to measure the amount of current present in it. In galvanometer, the pointer deflects on both the sides of 0 mark depending on the direction of current. So this is the construction of galvanometer. A coil is positioned between the pole pieces of a magnet in such a way that the pointer on galvanometer dial is connected to it. When a small current, for example 1 milliampere, flows through the coil will rotate and the rotation will be proportional to the amount of current passing through it. As we have seen in our previous slide, voltmeter and ammeter also work on the same principle. So in galvanometer, the pointer deflects on both sides of 0 mark depending on the direction of the current. So galvanometer indicates the presence of current in the circuit, whereas ammeter, it gives actual measure of current in the circuit. Nowadays, these test tools are used to measure two or more electrical values, that is digital multimeter. So basically, potential difference in volt, current in ampere, and resistance in ohm can be measured by using this digital multimeter. It shows the value directly in digits. Next, another interesting thing, which is electromagnetic induction. To understand this, let us discuss this experiment. A conducting wire is connected to this galvanometer. This is galvanometer and conducting wire is connected to it. And a magnet is placed in between these two as shown in figure. If we keep on moving this wire continuously, the pointer of galvanometer will show deflection. Now here we have not connected any battery in the circuit, but then also galvanometer shows deflection. Means due to the motion of this conductor near magnet produces current. If we keep that wire stationary and if we move magnet, then also current will generate. So if the wire is kept moving from A to B, the pointer of galvanometer gets deflected. Now move the magnet with the wire fixed, the galvanometer pointer still gets deflected. So here you can observe magnet is moving in this coil, produces the current in the galvanometer. So in the year 1831, Michael Faraday showed that an electric current can be produced in a conductor with the help of moving magnet. It's really interesting. So that is electromagnetic induction. Michael Faraday, he was an experimental scientist. He was not formally educated. Teenager Michael started working in a bookbinding shop. While reading books there, he got interest in science. Sir Humphrey Davy appointed him as a laboratory assistant in the Royal Institute, London. There he discovered the law of electromagnetic induction and the laws of electrolysis. Several universities offered him honorary degree, but Faraday refused to accept such honor. Now let us discuss this activity based on electromagnetic induction. In this slide, you can see three figures. Solenoid coil, battery, plug key are connected as shown here. And coil kept near to it is connected to galvanometer. So here is the galvanometer. In figure A, if we open plug key, no current will be there in the circuit. Galvanometer quickly comes back to zero. If we close plug key, current starts flowing through solenoid, which produces current in the coil, and pointer again deflects to other end of galvanometer. In second figure B, when the electric current is flowing through the solenoid coil and solenoid coil is displaced with respect to the coil, the current is still produced in the coil. So we can infer from this experiment that even if the solenoid is kept stationary, a change in current in a solenoid produces current in the coil. And if the solenoid coil is moved towards or away from the coil, we can see deflection in the galvanometer. If the displacement of solenoid is faster, the deflection of galvanometer pointer will be larger. So, if the current in a solenoid coil is changed, a current produced in the coil. If solenoid coil is moved towards the coil, then also current is produced in the coil. So, if a conducting wire is kept moving in a magnetic field, a current is produced in it. We have seen Faraday's law of induction. So whenever the number of magnetic lines of force passing through a coil changes, the current is induced in the coil. So in this animated picture, you can see this magnetic lines of force are cut by this conductor and you can observe the deflection in galvanometer. So that indicates current is induced in it. So this is given by Fleming's right hand rule. What is Fleming's right hand rule? Stretch the thumb, the index finger and the middle finger in such a way, of right hander, in such a way that they will be perpendicular to each other. In this position, the thumb indicates direction of motion of conductor, the index finger indicates the direction of magnetic field, and the middle finger shows the direction of induced current. So this rule is known as Fleming's right hand rule. Now let us discuss about DC and AC. Means what? Direct current and alternating current. A non-oscillatory current flowing in one direction in a circuit from the cell to the cell, such a current is called as a direct current, DC. As against a current changing in magnitude and direction after equal intervals of time, which is called alternating current. So in this figure, you can observe this direct current is moving in one direction only, and alternating current is changing its direction like this after every certain interval. So if you observe the graph of alternating current and direct current, so alternating current keeps on changing its direction every after certain time interval, and direct current, you can see the direction is same, it is not changing. So let us talk more about alternating current and direct current. So this is the difference between AC and DC. In AC, the magnitude of current changes continuously with time and the direction of current changes periodically. In DC, the direction of current throughout remains unchanged or same, though the magnitude of current changes with time. So this is the graph which we have already discussed about. AC is produced in power station, DC is produced by cells or batteries. AC can be transmitted to long distances, DC cannot be easily transmitted to long distances. In India, the frequency of AC is 50 Hz and frequency of DC is 0 volt. So this is very interesting part. Electric generator. Students, we have seen experiments on electromagnetic induction. In those experiments, the amount of current produced was very small. But same principle is used to produce large amount of current. So let us understand the construction and working of electric generator. So electric generator, mechanical energy is used to rotate the current carrying coil in the magnetic field around the axle, thereby producing electricity. So here you can observe this armature is rotated by mechanical energy, and this is how current will produce. In this figure, a copper wire ABCD is kept in between two poles of magnet. The two ends of coil are connected to conducting rings R1 and R2. These two are rings. Through carbon brushes B1 and B2. These R1 and R2 are fixed to the axle. Axle can be rotated. B1 and B2 are stationary and are connected to the galvanometer, which shows the direction of current. When the axle is rotated by using mechanical energy, the coil will also start rotating. Now, if coil ABCD rotates clockwise direction, branch AB will go up and branch CD will go down. By using Fleming's right hand rule here, the direction of induced current is ABCD. The induced current is proportional to the number of turns of copper wire in the coil. After half rotation, AB and CD will interchange their places, and the direction of induced current will be DCBA, like this. AB is always in contact with B1 brush and CD is in contact with B2 brush. So in first half rotation, the direction of current from B2 to B1 And in second half rotation, the direction of current will be from B1 to B2. So this repeats after every half rotation and alternating current is produced. So this is what we call as AC generator. So this is how we can observe in this animated image how alternating current is produced and deflection in galvanometer like this. We learned the difference between alternating current and direct current. So depending upon which type of current it produces, the name is given AC or DC generator. Now direct current does not change the direction in the external circuit. To get DC, instead of conducting rings R1, R2, split rings PQ are used over here. Because of this type of arrangement, the branch of coil going upward is always in contact with one brush and the branch going downward is always in contact with other brush. So this is the basic difference between AC electric generator and DC electric generator. So children, in today's session, we have learned about magnetic effects of electric current. In that, we have learned Fleming's left-hand rule, right-hand rule. Along with that, we have studied the construction and working of electric motor, generator, alternating current and direct current. So read it, revise it. Thank you.